Hello, everyone. Welcome to this first session of the Gamma seminar in this semester. Our speaker today is Javier de Lucas, and we'll talk about Lie systems and compatible geometric structures. So whenever you want, Javi.
Okay, so thank you, Xavi. I don't know if I have to thank for the invitation, but anyhow. Today I'm going to talk about Lie systems. I will give an introduction to them. Yes, in short, Lie system is a special type of differential equation that has lots of interesting properties, and it can be related to many problems in physics and differential geometry. Even not straightforwardly, it can be interesting for looking for applications and things like that. Normally, Lie systems are rare. Most of differential equations are not Lie systems, but it happens that Lie systems used to describe very important problems in physics and in mathematics, and that's why it is so interesting to understand, to study them from a physical and mathematical point of view. So let me tell you as a curiosity that the Lie systems were discovered and analyzed for the first time mainly by Lie, Königsberger, Gulber, and others. And after being studied toward the end of the 19th century, they draw not much attention till the topic was recovered here, where I'm now in the school and the Centre de Recherches Mathématiques of the University of Montreal, where Winternitz and all the collaborators saw all the application of this system. They wrote, I don't know how many, 40, 50 papers on the topic or even more. So what I plan to do today, okay, and I will be doing for 3 weeks, will be first to analyze the origins of Lie systems, to explain what a Lie system is. I will explain you the main properties, and then I will move to the classification of Lie systems. I will tell you how to describe all possible Lie systems. I will also tell you about open problems, relevant open problems I'm working on. And I will give in this talk mainly 2 approaches at the beginning, 2 approaches to Lie system. One, which is focused on Lie group actions, and another one that is focused on the Stabios distributions and bundles. At the very end of these topics, I will start studying Lie systems along with geometric structures. So let us start. So let me introduce you what a Lie system is. Okay, so let us start by a very easy example, a Lie system and superposition rule. Okay, you already know that a differential equation like one, okay, like this one, on the real line, and non-autonomous, I mean time-dependent, is such that a general solution can be described as a particular solution of the whole differential equation, okay, homogeneous, and a particular solution times a constant of the homogeneous differential equation relative to this. I mean, everyone knows that every physicist knows that to solve this, the first step is to drop this non-homogeneous term to solve this part, yes, with A2, okay, and then by the method of the dependence of variables to obtain a solution of the general one. And then the general solution can be always written like this thing, that is a solution of the general differential equation, the global, and then this thing is a solution of the homogeneous part times constant. And the general solution can be written in this way, okay? And now this thing in here, that it is a solution of the homogeneous part, it can be written always as the difference of 2 solutions of this general differential equation. Because if you have 2 solutions of this inhomogeneous differential equation, the difference between them will give you a solution of the homogeneous part. This is very easy. So using these tricks, what you can obtain, you can prove, is that the general solution of equation 1 can be written as this, okay? This expression, which depends on two particular solutions of this differential equation and a certain constant, k, that it can vary. Everyone knows more or less that if you fix these two particular solutions for different values of k, you will obtain particular solutions of the general equation with different initial conditions. So somehow this k, which is a parameter on R, is related to the initial condition of this differential equation. Okay, so this thing in here is what is an example of what is called a superposition rule, sometimes called also a nonlinear superposition rule for a differential equation. It's a way of writing the general solution of this differential equation as a function of a certain set of particular solutions, here x1, x2, and a certain constant that somehow is related to particular to initial conditions. So, and also you can take into account that this expression here does not depend explicitly on time. I mean, the time only appears as a parameter for the particular solutions. That's all. Okay, so it is readily known, and it's quite difficult to prove it. I did it with my PhD thesis, that probably it was Abel the first one who was interested in looking for those differential equations for which the general solution can be written as a particular function of a set of particular conditions and a parameter on the real line. I mean, you start by a differential equation of this type on the real line, non-autonomous because it depends on time, and you are wondering which is the most general form of this time-dependent function, x times x, this thing here, in such a manner that for this differential equation too, the general solution will be some function of a set of particular solutions and a constant, okay? So Abel thought of it for some time, but the reference to Abel doing so is just an indirect one. The first real works on the topic are due to these three guys, Gulbert, Daciot, and Königsberger. Okay, so they were from France, and Germany, I think, maybe the Prussian Empire at that time. So for 10 years, they were working on the problem posed by Abel, and finally, they said that if you have an nonautonomous differential equation, the real line, and it turns out that the general solution of the differential equation can be written as a particular solution of several particular solutions and a constant related to initial conditions, they prove that if the differential equation is analytic, if the expression is analytic, the differential equations must be of this sort. Additionally, they assume some technical conditions on it. And I will tell you that even nowadays, it's not clear which is the solution of this problem, assuming that differential equations is just smooth, that it's not analytical. This is an open-up problem that I'm solving now. So the thing is, for Riccati equations, it is known that the general solution of the equation can be written by means of three particular solutions, three different ones, and a certain constant related to initial condition. And the expression is here. This is something that it was done in 1893. The interesting thing is that 13 years before, in 1880, Lee proposed, well, published a book where he, for the first time, proved or showed his theory about Lie groups for differential equations and Lie algebras. So it turns out that in 1893, Gulbert obtained the most general solution to this problem. It was the one who said if the right-hand side of a differential equation, first of the differential equation is analytic, non-autonomous, the most general case of a differential equation meeting a superposition rule is locally diffeomorphic to a Riccati equation. That means up to a change of variables. But he was not he has not very good luck, because indeed in 1893, Lie noticed this result by Kullberg, Berciot, and Königsberger, and he told them, he said, indeed, he wrote a paper which was published as a couple of pages after the original one by Kullberg. Indeed, the Kullberg is this one, Compte de mathématiques à Sciences Paris, and as you see, 1893, pages 964, 965. Here, Kullberg says that the most general differential equation on the real line being analytic, which has a superposition rule, is up to a change of variables, the Riccati equation. And Lie knew about it and wrote a paper that you see in the same journal, just 300, almost 300 pages afterwards. And, well, he wasn't very kind. Okay, this is that Lie noticed that the right-hand side of the Riccati equations, these coefficients in here, 1x squared, they were pretty much similar to one of his results. Lie was characterizing Lie algebras of finite-dimensional Lie algebras of vector field on the real line, and these coefficients are exactly those that he found for the most general Lie algebra of analytical vector fields on the real line. He found these three vectors. He found these are the commutation relation with respect to the Lie bracket. And it turns out that Lie said, come on, this reminds me of this thing. And immediately he noticed that the works by Kullberg, Berciot, and Königsberger, they were just trivial applications of one of his ideas. Indeed, he wrote what is green here. This is indeed extracted from Lie's work. Si je ne me trompe, je suis parvenu à démontrer d'une manière rigoureuse et simple que mes systèmes sont ceux qui possèdent la propriété demandée. What it says is that if I'm not wrong, I will show in a rigorous manner that the system 2, this one here, are exactly those that admit a superposition rule. So let me explain what is this. This is non-autonomous because it depends on time, first order system of differential equations in normal form, because the derivatives are on the left-hand side and they can be written out of things that depend just on time and on the variables. So he said that given this thing, okay, which is defined on Rn, it's not like Kullberg, Berciot, Königsberger result that is just on the real line. He said that if you have such a thing, such system of differential equations, if you want to know if such a thing, such a system of differential equations admits any superposition rule, okay, what you will notice is that these functions in here can be gathered together to obtain R vector fields. You see, these things with I, they are the coordinate xi of an independent vector field. The vector field is parameterized by the index alpha, and you have R of them. And he said that if this system 2 has a superposition rule, it's a necessary and sufficient condition to obtain a superposition rule that this vector field will span a finite-dimensional G algebra. That means that the commutator of two of these vector fields will be a linear combination with several constants of the elements of these vector fields. And it must be said, very importantly, that these must be constant. So Lie defined the systems, and he said, after Kullberg's work, that he thinks that those systems admitting a superposition rule are exactly those of this form. In particular, this thing, the right-hand side, this thing in here, these coefficients, are indeed the coefficient of these three vector fields, which close a certain Lie algebra vector field. So this Riccati equation is a particular case of these systems of differential equations. Okay, so what Lee said is that these systems and meta superposition rule, they are very important because they are characterized by means of Lie algebras of vector fields. And this links Lie system superposition rule with the theory of Lie algebras, and in particular with the theory of Lie algebras of vector fields and manifold. So that's why Lee was so interested at the beginning in this problem, because it was a very easy application of his theory that showed that three guys could be making research for 10 years for something that it could be proved in 10 minutes. So this is what he did. And this is what nowadays is called the Lie theorem. So the Lie theorem just says that if you have a differential equation system of differential equations form, it is just the differential equation here is nothing but first order system of differential equations in normal form. Then this thing, this system, we have a superposition rule. I mean, a way of describing the general solution as a particular function, time-dependent function of a particular set of particular solutions and some constant, if and only if it turns out that the right-hand side of this system differential equation can be written as a linear combination with time-dependent functions of certain coefficients that belong to certain Lie algebra of vector fields. This was a conjecture. It was conjectured by Lee after Guldberg's work, was finally proved in the work by Lee and Cephas in 1893. This is a very famous work where you can find many, many important results about the theory of Lie groups and the theory of Lie algebras. So these appear in those works like a simple application. Okay, it is one of the parts of this work. It was stated that these systems are those that they have a superposition rule. One comment. Normally, Lie systems are called Lie-Cephas systems because Cephas published this paper where this famous theorem is, and this theorem is also called the Lie-Cephas theorem. But let me tell you that Cephas did maybe nothing after that work about Lie systems, and I think that it was, as far as I remember, one of Lie's students that was devoted to write down the notes from the course by Lie, who was not especially good at making courses or writing research. Okay, indeed, nowadays we still have problem with his work because they are pretty much obscure points, and there is no way of knowing what he has done. Okay, but it's not about having mistakes. It's about the fact that in some parts of the proofs are not clear, and many researchers have had problems for the last 10 years trying to figure out what happened, what he did. So let us recall now, let us explain this more carefully, okay, for the Riccati equation, and just see that this is the so-called Riccati equation, yeah? And as I told you, the coefficients here will be related to 13 vector fields. Sorry, this is a typo, this would be Ex squared. And when you work out the Lie brackets between these vector fields, you obtain a finite dimensional Lie algebra. You say that when you you calculate the Lie bracket of two vector fields, what you obtain is a linear combination of the elements of this Lie algebra with just constants, okay? So after seeing that Lie knew much more about systems and Mitterrand superposition rule than themselves, Bessiot and Guldberg decided after Lie's work to coin the term Lie system for those systems of differential equations, non-autonomous system differential equations in normal form, having a superposition rule. Okay, so this is more or less the initial story about these Lie systems. This happened toward the end of the 19th century. Bessiot keep on working on the topic for something like 30 years, 20, 30 years. That's why also Lie systems are called sometimes Lie-Bessiot systems. He obtained many results. Most of them, they are on a, it is impossible or very difficult to get them. So we can say that many of his results were lost. Okay, some of them they are just my PhD thesis. I managed to find them in well, somewhere talking with people from the institute, the Center of the Research Mathematics, University of Montreal, who was devoted to this topic. Okay, but anyhow, toward the 80s of the 20th century, Winternitz, Harnad, Véronique Hussin, Snyder, there is a big Grunland and others from the institute where I am now. They developed this theory much, and they found many applications of Lie systems in integrable systems, in mathematical physics, in Backlund transformation, parallel bit transcendence, discrete systems, super differential equations. Everywhere you can imagine, at every possible field you could find applications of these systems. So they were pretty much useful. And if the theory by itself of Lie system was at certain moments not that interesting, the applications in other fields were even more interesting than the Lie system concept itself. So this motivated a big advance. People from the SURIAM, I mean this center where I am now, they were more interested in applications than in the mathematical development. The mathematical development came from Grabowski, from the Institute of Mathematics of the Polish Academy of Science, Marmo, from the Institute of Nuclear Science in Naples, from Cariñena, the University of Zaragoza, and other related researchers, like myself, that I have, I don't know, maybe 50 or 60 papers on this topic or something like that. So we developed this more geometrically, and these techniques allow it to solve many problems in the theory of Lie system in a more elegant way. So the main object, the fundamental object to describe Lie systems is a time-dependent vector field. Okay, it's a little bit specific because with differential equations, one used to prefer to use jets and other stuff, but it happens that when it comes to Lie system, the good technique, the good way of doing so is by defining a so-called time-dependent vector field. In short, a time-dependent vector field is just a family of vector fields parameterized by means of a parameter. That's all. I mean, all what you have in here, all this stuff, is just to say that a time-dependent vector field is nothing but a T-parameterized family of vector fields. The way of saying that in a geometric way is that time-dependent vector field is the mapping from R times n to the tangent bounded to n in such a way that the following diagram is commutative. Okay, so you see that if you fix T, okay, and you have a point X, and you have the value of the time-dependent vector field, this point T and X, and you project, I mean, what you are doing here, the commutativity of this diagram tells you that pi with X must be pi 2, but pi 2 is X. So it tells you that for every T, the projection of this thing must belong to X. So it means that this thing belongs to the tangent space to X. So when you fix T, the time-dependent vector field for every value of the manifold M gives you a tangent vector. So it is a family, is a vector field, and with different values of T, you obtain different vector fields. And the other way around is also true. You have a family of time-dependent vector fields. You can define a time-dependent vector field as a mapping of this way. So this is equivalence. So when you talk about time-dependent vector fields, okay, you will use them to describe Lie system. How is it going to happen? Okay. A time-dependent vector field is a kind of special vector field. So there is a notion of integral Q, okay, for a time-dependent vector field. It's pretty much similar to what happens to standard vector field. So it's a mapping from R to N in such a way that the tangent vector of this mapping, this curve at time t, is given by what? The value of the time-dependent vector field at the time t and at the point gamma of t. So this thing in here is the differential equation describing the integral cubes of a time-dependent vector field. If you write this in coordinates, writing xi for the coordinates of the cube gamma, what you obtain is this system of differential equation. So what it's saying is that when you have a time-dependent vector field, you can write the differential equations, the system differential equation describing the integral cubes as this. I mean, a system of a sorted differential equation in normal form. Okay, and you can see that these things are indeed the coordinates of the time-dependent vector field. And you can do it the other way around. You can type a time-dependent vector field that is nothing but a standard vector field in the manifold N, whose coefficients depends on time, because for every time you have another different, and then consider these things as the coefficients of a third-time system differential equation. So you see, given a time-dependent vector field, you have one of these, and given one of these, you can obtain a time-dependent vector field. So geometrically, okay, we try to understand Lie systems by means of time-dependent vector field. And we make an equivalence from now on. When you see a system of this type, okay, you will describe it geometrically by means of the time-dependent vector field associated with it. And the other way around, if you have a time-dependent vector field, and you talk about the system X, it means that you are talking about this thing. This makes all the notations quite much more easier. So now you can remember that for a Lie system, you have that the right-hand side should be linear combination with time-dependent coefficients or certain coefficients that are the coefficients of vector fields spanning Lie algebra vector fields of the infinite dimension. So you can, using this, the Lie theorem is as easy as saying that X, the system, is a Lie system if and only if the time-dependent vector field can be written in this way, with time-dependent functions, and certain vector fields which span an R-dimensional Lie algebra vector field. These Lie algebra vector fields will finally coin a Bézier-Goulbert Lie algebra vector fields. And I gave this name that is, well, everyone uses it, because it was Bézier, Goulbert partially, but mainly Bézier was the one who, after Lie's theorem, used this Lie algebra to study Lie systems and many other properties. Okay, this is a very important part of Lie systems. Indeed, I can tell you that Lie at the very beginning, the initial idea of the world theory by Lie, it was to use group theory to study differential equations. Okay, he was inspired by Galois theory for polynomials, where a group, the symmetries of polynomial, tells you can solve it by means of elementary operations. And Lie wanted to use groups to describe differential equations. And this is one example of what he did. So Lie did lots of things, okay? Not exactly about Lie systems, but about topics that it turned out to be very, very important to other fields, to Lie system for course, but other things. So what he did, he classified all finite dimensional Lie algebras of complex vector fields on C and C2, okay? Also classify all Lie algebras of analytical vector fields on R. It's not written, but it's a Dirac equation. I said that it was done by Goulbert and all this. So he just retrieved the result. Then by means of a trick, was able to classify all finite dimensional Lie algebras of vector fields on R2. And now, partially, Lie said that he managed to solve the classification of finite dimensional Lie algebras on R3 and C3. Well, Lie said, we don't know if it is true and if these calculations exist or were lost or whatever. The only thing that it is known is that part of these results and in Lie's work, one of the Lie's works, that the remaining calculations are lost. We have no idea how to solve it. I have some conjectures about how to solve this problem. Indeed, it can be a breakthrough, but it's difficult to prove. And let's say that this kind of research it can be tricky. Normally, having an idea means nothing. It's something that has to be proved. Well, it's a very interesting problem. And in general, the word classification of Lie has a little problem. Lie's results are, of course, brilliant. But the problem is that he wrote this at the end of the 19th century. So the knowledge of differential geometry and problems, it was, well, most of things they were not known, and the language is quite archaic. It's the statements are not precise, conditions are not clear. Well, at the very end, no one finds anything wrong. Yeah, but the problem is that when people try to understand what Lie did, well, it happens what it was written in here in this paper, but González López from the Autonomic University of Madrid, I think, Nicky Canra from McGill is here from Montreal, and Peter Olber from Minnesota. So in this work, Lie algebra vector fields on the real plane, he studied again the Lie's classification of finite dimensional Lie algebras of analytic vector fields on the plane, and he did it very well. They explain all problems or skew points, everything, and he solved lots of problems because, as it was written in the paper, the interpretation of Lie's work led to many problems. I mean, these results the results by González, Cameron, and Olbert, clear up some confusion and contradictory statements in the literature on this problem. I mean, the classification of Lie algebras of vector finite dimensional Lie algebras. The classical authors, for example, Lie, Camp, Bianchi, etc., never really made it clear whether they were working on the real or the complex numbers. Sometimes it's not even clear if they are talking about the smooth or analytical ones. And the assumptions, I can add that they are not clear neither. So it's really a hard work to understand what is going on. And there are several examples about misunderstood led by Lie, Campbell, and Bianchi's problems on their works. Okay, so let us say that essentially what Lie did and other researchers did, it's okay once you state the proper assumptions and once you clarify certain points. So it is okay. Without these assumptions that are not known for Lie, or Lie just made it without noticing, okay, things become tricky and works by Lie can be extended significantly. Okay, you can find many results. I mean, it's important to stress that technical details, changes, these technical details and Lie's work and other researchers' works lead to important advances, okay, in several theories. So let me explain you that on the real line, as I said, Lie said exactly that every Lie algebra, finite dimensional Lie algebra of vector fields on the real line of analytic vector fields is up to a change of variables at a point where one of the vector fields does not vanish, locally mappable, can be changed into a Lie algebra or Lie algebra of these Lie algebra of vector fields. What I just said is just the complete full in details result. If you drop just one detail, this is not true any longer. Okay, and indeed, what you can obtain, it can be perhaps pretty much different what it isn't here. For example, on the real line, there are lots and lots and lots of different types of Lie algebras, and they don't need to be SL2 or subalgebra of SL2. This is to start with. Okay, even you can obtain Lie algebras of the dimension you want. Okay, and this is just by saying that the vector fields are smooth and non-analytic. So as I said, technical details here are very important. Okay, so after that Lie first, and then González and Cameron managed to go through Lie's classification of the researcher classification and give the full classification of finite dimensional Lie algebras of vector fields on the plane. So he found that there are 28 families of Lie algebras. You have a Lie algebra finite dimensional Lie algebra analytic vector fields. Locally, there is a change of variables that it maps to one and only one of the families given here. Okay, and this exhausts all possible Lie algebras. But take into account that you have 28 families, and some of these families depend on parameters. For example, this depends on R. Several Lie algebras depend on a parameter alpha, that is a real number. Some functions depend on arbitrary functions of functions which are solution of a partial differential equation. It's a real suit. There are lots and lots of things. And the thing is that for every Lie algebra on this classification, you can find very important applications. For example, for SL2, complex Riccati equation with that dependent coefficient, it appears in diffusion equation, financial model. With SO2, you have trigonometric mechanical systems on the plane that they appear in Hale's theory. You have time-dependent harmonic oscillators with or without dissipative terms. You obtain Riccati equation with complex coefficients, second-order Riccati equations, Kummer-Schwarz equations, Schwarz derivative which appears in string theory, Miller-Pin equation which appear in quantum systems, or they appear also in the description of the motion of certain mechanical systems. It's huge, okay? So what I did a long time ago was to put some order of these Lie algebras. So one of my most works, and it was published in one of the best journals in the world, Journal Differential Equations, in mathematics is maybe the 15th or 10th out of 300, so it's pretty much good. What I did was to make some order. I mean, for every letter in here describes one of these Lie algebras, finite dimensional Lie algebras on the plane. So part of my work was to show that all these Lie algebras are not independent, and some of them could be proved to be diffeomorphic. I mean, a change of variables map them into a Lie algebra of another Lie algebra of vector fields. So when you do so, you obtain lots and lots of applications of relations between these Lie algebras. Okay, and the fun thing is that when one Lie algebra, for example, one of this class, up to a change of variables becomes a Lie algebra of another one, that is one of these arrows, you obtain that the 28 families can be considered as pieces of particular families of Lie algebras. Indeed, P7 contains P4, P1, ER1, 14B, E2, E14A. You see, you only have to follow the arrows, yeah? So, and this is not including any other one. If you do with other ones, you will finish at P8. If you do with other ones, you will finish at I11. And if you follow the remaining ones, you will finish at I20. So this work said that there is essentially no 28 families of Lie algebra. There is just 1, 2, 3, and 4 families. The thing is, this was not fulfilled because these Lie algebras are quite complicated. So this thing was a theorem for some of these Lie algebras, and for I20, this was a conjecture. It seems that this is maximal, but it's not clear. And also I gave a characterization of what are these Lie algebras, okay? So P8 and I20 are Lie algebras of so-called projective vector fields with respect to a flat metric, okay? This was Riemannian and this was pseudo-Riemannian, and on the plane, essentially, there are the two possible cases. One second, I think so. Well, I don't remember exactly the details. I think so. And two Lie algebras were Lie algebras or of conformal vector field with respect to a metric. Okay. So let me think. I think that the conformal ones with P7 and P8, and the Riemannian, pseudo-Riemannian, they were I11, I20 projective. I think so. I don't remember exactly the details, but there are 4 families. So the natural conjecture in this topic is to say that you will do the same for 3-dimensional manifolds, and it's a thing to be done. Okay, so far as I could check the problem, it seems so, but I'm not sure, and probably I will never be sure absolutely. But well, work in this this direction is being done. So the thing is that let us change a little bit the topic, and we are talking about the possible applications, the possible approaches to study systems. And there are two main approaches, one given by Lie theory, another one given by distribution. And the two approaches were used by Winternitz, but he didn't care much about the mathematical theory. He was more interested in applications there. He has a lot of results, but they are not precise, they are not well stated, but they are very useful, and there are lots of applications. And he essentially knew everything. I mean, the main ideas of these two approaches. Okay, but from the Lie group approach, because every Lie system can be related to a Lie group and a Lie group action, these were developed mainly by Poisson toward the end of the 19th century, the beginning of the 20th. And the Poisson's approach that was developed by Kariniana, Marmot, and Grabowski toward the end of the 20th century, and myself during the 21st century. I must say that it depends on the problem. Both approaches are useful for different things. Okay, but well, let us leave this way because it's the most interesting thing. Okay, so I will explain shortly both approaches, and this will finish my talk today of introduction because this is the most important thing to say at the beginning. Okay, so it turns out that when you have a Lie system, you will obtain a certain differential equation in a Lie group. This is the idea about the show that is based on works on results by Lie. And okay, consider you have a Lie system in a manifold M, and you have a Jacobi Lie algebra B. You remember that this is B is just a finite dimensional Lie algebra vector. Yeah. So it's a result by Lie. So when you have a Lie algebra vector fields, finite dimensional Lie algebra vector fields, you can describe a Lie group action. G is a Lie group acting on the manifold, whose fundamental vector fields will be those of you. Here there are some technical conditions, but I can tell you in practice that these technical conditions in general are not necessary, are not important. So let's go with this. And you have this Lie group action. And the main thing is that the Lie algebra of the Lie group, tangent space to the neutral element of the Lie group, will be isomorphic to the Lie algebra. Okay, so what happens is that when you pick up this Lie group action and you pick up a basis of the Lie algebra of the Lie group, let's say A1, AR, okay, and you obtain the fundamental vector fields of the Lie group action this way, you will obtain these vector fields of B, okay, by definition, because this is the Lie group action related to the Lie algebra B. So when you work out the fundamental vector fields, you will obtain, they will be those spanning B. Okay, so note the following thing: your Lie system, okay, defined by a time-dependent vector field X, is always a linear combinations with time-dependent functions of a certain family of vector fields that belong to the Jacobi Lie algebra. They are a basis of the Lie algebra. So you have something of this sort. But also, okay, you can understand these vector fields here like the fundamental vector fields of the Lie group action. So what we are going to do is to use the Lie group action to construct a Lie system or Lie group, recovering the solutions of the Lie system. So when you have your Lie group action, when you fix a point of the manifold, you can describe an action, a mapping, from the group to the manifold this way. For every element of the group, this mapping will go to the action of G on that element X. Okay, so once you fix this, you have a morphism of this type. So when you write the fundamental vector field, the formula, this, what you have in here, this thing, is phi X acting on the exponential minus T A alpha. And this thing here is the parametric, the one parametric subgroup related to the element of the Lie algebra A alpha. So what you have in here in reality is the tangent mapping of phi x at E at the neutral element of A alpha with an int. So it turns out that every element of this here, every vector field at a point x can be written like the tangent map to this mapping of an element of the Lie algebra. So if you use that, remember that this thing, your Lie system at a point t and x, is a linear combination with time-dependent functions of a family of vector fields. Yeah, but this thing in here, the value of the vector field x alpha, the point x, can be written using the previous formula. And summing up everything, what you obtain is that you can describe the value of the time-dependent vector field at x like the image of the tangent mapping to phi x of a certain curve. And you can notice that this curve is the same for every point of x. Okay, you always have this curve. Okay, and whatever the point x is, the only thing you have to do to obtain the new expression is to change the x. So you obtain in a natural way an element of the Lie algebra of the Lie group, a curve of the Lie algebra. Yeah. So when you start by means of things, this time-dependent vector field, this expression for the time-dependent vector field, which is a linear combination of the elements of a basis of the Bézier-Group Lie algebra, it gives you another combination in the Lie algebra of the group. And this is one-to-one. So once you do so, you can describe the following differential equation of the Lie group. G now is an element of the Lie group, and A of t is a curve in the Lie algebra, the one given before, and this in here is the tangent map to the right-hand action of the element G. And this, for every time t, what is on the right-hand side of this equation, everyone knows that this expression of a right invariant vector field. So using this, at the very end, what you obtain is that your equation of the Lie group, the right-hand side, can be written as a linear combination with time-dependent functions of a family of vector fields, right invariant vector fields on the Lie group. But you already know that these vector fields, right invariant, they close also a finite dimensional Lie algebra vector field. So this is also a Lie system, but on a Lie group. Lie systems or Lie groups of this type are called automorphic. And the thing is that using this automorphic, this proposition, and I will finish here, tells you that if you solve the automorphic Lie system and you obtain a solution crossing by zero at the element and the neutral element, okay, let us call G of t, and this is the induced Lie group action of a Lie system, the general solution to your Lie system can be written as the action acting on a fixed point and by means of the solution of the automorphic Lie system. This is what this proposition says. I will continue next quick because it's, we are really running out of time. And so the expression tells you that every Lie system on any manifold can be solved by means of a particular solution of a particular type of Lie system on a Lie group. And that's why these Lie groups are so important. And in many methods, for example, numerical methods, it's very useful to reduce the study of every Lie system to study these automorphic Lie systems. They appear in many applications. Indeed, it is interesting that if you solve an automorphic Lie system, you can see that changing the Lie group, okay, action, you can relate this curve with other Lie systems in other manifolds. All of them will be solved by means of this equation. Okay, this is a good moment to stop. So it's ready. There is 10 in the night. So thank you for your attention. I expect that this was interesting for you.
Thank you very much, Javi, for your talk. Are there any questions or comments?
Yeah, I have a question because I didn't understand the last part.
Yeah.
This automorphic equation, it's related to the particular Lie group? Or
Yeah, I mean, somehow, yes. I mean, when you have a Lie system and you have a Bessel-Gilbert Lie algebra, the Lie algebra is a Lie algebra of a Lie group. So you can, on that Lie group, construct a Lie system. Okay. There are several types of Lie groups with the same Lie algebra. Yeah. So this equation, the automorphic, can be constructed theoretically only for the Lie group that is this. How it is called? Sorry. The first homology group is trivial. I mean, is so connected? No, is. Well, I'm sorry, I don't remember now the word in English. I mean, it's that every curve is a homotopy equivalent to a point. This is the real definition. So you can, for every Lie system, define a Lie on that Lie group. And the way of describing the Lie system gives you a curve on the Lie algebra that characterizes this equation. That answers your question, or you?
Sorry, I'm also tired. Can you repeat the last sentence?
Yeah, I mean, when you have your Lie system, your Lie system, you have a Lie algebra.
Yes.
And this Lie algebra induces a Lie group, which has this Avon theorem. Yeah, well, Lie algebra, and there's the Lie theorem. Okay, so on that Lie group, you can construct a Lie system whose form is uniquely defined out of the form of the Lie system original of the manifold. I mean, if you start by the Lie system with these coefficients, okay, with this basis, on the Lie group you will have.
Okay. Yeah. So the Lie system is in.
Yeah,
here.
this is the system on the manifold, and these things are vector fields that they close a certain Lie algebra structure. What you do is just to pick up certain elements of the Lie algebra of G that they close the same constant structure.
Okay.
And to create this right variant in vector fields are those, okay, given by these vector fields, and the coefficients are the same as before, but with a and you can drop this sometimes.
The solutions are very different, changing the coefficients. I mean, if I have to do two Lie systems with the same Lie group or Lie algebra, but they have different coefficients.
I mean, they can be very different. The idea is that depending on the Lie algebra you have, if the Lie algebra here is solvable, you will be able to solve this problem. Okay, so no matter where the coefficients are, there is a method to obtain the solution. Yeah, there is no problem. This is what Lie wanted, that with certain Lie group associated with differential equations, if the group is solvable, the equation can be integrated. But if the group is not solvable, okay, it's up to the coefficients. Okay. I mean, different coefficients, even coefficients that are pretty much the same, but they can have different derivatives at points or things of the sort. They change absolutely everything. It's every case is something different, so you have to take care of that. It's quite difficult.
Okay, thank you.
You're welcome.
Any more questions, comments? No.
Just one comment, last comment. I mean, what I have found in this is that whatever your research is devoted to, you can find examples of this, and they will be interesting. I mean, if you are working on k-contact, there will be examples where Lie systems related to a k-contact structure, they will appear. If you are interested on Lie groups, the properties of Lie groups will be used to study the integrability of these differential equations. If you are working on distributions or connections, you can construct them by means of these Lie Bessel-Gilbert Lie algebras and to start to integrate these systems. And sometimes when you work on Lie systems, for example, about Lie algebras, finite dimensional Lie algebra vector field, then it will have applications in our field. So it's quite everything in here. It can be applied to many different subjects: super geometry, discrete system, numerical systems, whatever.
Multisymplectic.
Multisymplectic. All geometric structures can be studied with this, and all geometric structures can be used to study the systems. Thank you.
Okay. Any more questions, comments, remarks? No? Okay, so thank you very much, Javi, and thank you all for attending, and see you all next Thursday at the same time for the second lecture on this course on Lie systems.
With geometric structure. Well, the distributional and geometric structure. So thank you.
Thank you.
Oh.